Hello everyone, I am Dr. VRAO. In the lecture 60 of thermodynamics or from the lecture 60 of thermodynamics, we came to know that any process which involves decrease in energy or increase in randomness occurs spontaneously. I repeat, any process which involves decrease in energy or increase in randomness occurs spontaneously, right? So this randomness, this increase in randomness, in thermodynamics terminology, this increase in randomness or this randomness is termed as entropy, right? That randomness in thermodynamics terminology, that is termed as entropy, right? Okay, so and entropy is defined as now we can define the entropy. Entropy is defined as a property of the system which measures the disorder or randomness in the system, right? I repeat, entropy is defined as a property of the system that measures the disorder or randomness in the system, and usually it is represented by a letter S. It is represented by a letter S. Okay, and like internal energy and enthalpy, like internal energy, like enthalpy, entropy is also a state function and it is a extensive property, right? It is a state function and it is a extensive property. So as the entropy is a state function, so we can write the change in entropy as delta S, because entropy S is a state function. You know the state function that depends on initial and final states of the system. So change in entropy, we can write the change in entropy as delta S, and this can be calculated by using entropy in the final state minus entropy in the initial state, right? That is randomness in the final state minus randomness in the initial state, right? So this is about entropy. So we know that entropy is a measure of randomness, it is a measure of disorderness. We all know all these definitions, but we all should know that from where it was derived, Actually, it was derived from this state function, or this extensive property is derived from Carnot cycle, right? What is that? Carnot cycle. Do you know the entropy or a state function is derived from Carnot cycle, right? Carnot cycle, right? So that state function, that new state function or that an extensive property is derived from Carnot cycle. Carnot is a scientist, right? He proposed a imaginary cyclic reversible process to describe the maximum conversion of work into heat. I repeat, Carnot is a scientist, right? Carnot is a scientist. He proposed an imaginary cyclic reversible process to describe the maximum conversion of work into heat, or heat into work, maximum conversion of heat into work. Actually, what is this Carnot cycle? In this Carnot cycle, 1 mole of ideal gas is subjected to 4 sequence operations. 4 sequence of operations usually we called as 4 strokes. Which includes isothermal expansion, which includes that 4 strokes includes isothermal expansion, right? Adiabatic expansion and isothermal compression and adiabatic compression. So these are the 4 strokes or the 4 operations made on 1 mole of ideal gas, right? When we actually, I don't want to go through the derivation of Carnot cycle, but I want to conclude the what is the ultimate equation in the Carnot cycle, right? So when we are deriving the Carnot's theorem, actually the basic essential point in the cyclic process or the basic point in the cyclic process is that net heat absorbed is equal to net work done, right? So the basic point of Carnot cycle or the essential principle involved in cyclic process is that net heat absorbed is equal to net work done, right? So net heat absorbed, net heat is equal to net what is it called, net work. That is, those two should be equal, right? So net heat is equal to net work done, but that is when we are deriving the Carnot's theorem, ultimately we get the equation that is what is that equation? That equation is W is equal to Q2 into T2 minus T1 by T2, T2 minus T1 by T2, where T2 is the temperature of the source and T1 is the temperature of the sink, right? And Q2 is the heat corresponds to the temperature T2, right? So where T2 is the temperature of the source and T1 is the temperature of the sink, and you should be kept in your mind that T2 is always greater than T1. T2 is always greater, that is temperature of source is always greater than temperature of sink. So T2 is greater than T1, right? So this is the equation that we get when we are deriving the Carnot cycle, when we are deriving the Carnot's theorem, okay, where T2 is the temperature of the sink. You should keep one point in your mind, T2 is the temperature of the source and T1 is the temperature of sink, and T2 is always greater than T1, right? So, and by when we observe this fraction, that is T2 minus T1 by T2, okay, it is always less than 1, because T2 is greater than T1, this fraction should be less than 1 always, right? So this fraction always less than 1, that means W is always less than Q2. W is always less than Q2. For example, if you take T2 as 5 or T1 is 3, then 5 minus 3, that is 2, 2 by 5, that is also equal to less than 1, right? That is less than 1. So this fraction value should be less than 1, that means W is less than Q2, okay, that is W is less than Q2, that means work done is less than heat absorbed. From this equation we can conclude that work done is less than heat absorbed, and that heat absorbed is, that is the heat absorbed at Q2, that is Q2 is heat corresponds to the temperature T2, that is T2 is temperature of source. So the work is always less than heat absorbed, and where Q2 is heat corresponds to the temperature T2. Heat corresponds to the temperature T2. Okay. So W is less than Q2. That means heat is work is always less than Q2. From this we can conclude that only a part of heat is converted into work, or the only a part of heat absorbed or part of it corresponds to the temperature T2 is converted into work, right? Okay, so because you actually when we are deriving the equation, there is Q1 is missing. Actually Q1 is the heat corresponds to the at a temperature T1, right, and Q2 is the heat corresponds to the temperature T2. Okay, so from this equation we conclude that a part of heat is converted into work. Ante that means part of heat corresponds to the temperature T2 only can be converted into work. But what about the what about the heat absorbed at temperature T1? That is remaining, that is Q1 heat absorbed at temperature T1, or the temperature corresponds to heat, or heat corresponds to temperature T1 is given out by the system to the surroundings. So what you should keep in your mind is that only a part of heat is converted into work, and that part of heat absorbed at T2, that is part of heat absorbed at T2 only can be converted into work, and remaining portion of heat, that is heat corresponds to the temperature T1 given out by the system to the surroundings. Okay, that means we can make a bold statement that not all the heat is converted into work, right. So this is the reason why superheated steam is used in steam engine, right. Superheated steam is used in steam engine. Actually in the steam engine we are using superheated steam. We are using superheated steam. So a part of superheated steam is only converted into work. But what about the another portion? That is a fraction of superheated steam is only converted into work. But what about the remaining fraction of superheated steam? So this is the reason why superheated engine operates, that is superheated steam is used in steam engine, right. Superheated steam is used in steam engine, that is that superheated steam is useful to do some work, that means a portion or a fraction of superheated steam is only useful for work, right. So we can go for the efficiency of the engine, that is a fraction of heat absorbed by the engine which can be converted into work is called efficiency, right. A fraction of heat absorbed, a fraction of heat absorbed by machine which can be converted into work gives the efficiency of the engine. Okay, so efficiency which is represented by letter eta. Okay, efficiency, what gives the efficiency? The fraction of heat absorbed by heat engine which can be converted into work gives the efficiency of the engine, that is fraction of heat, that is W by Q, that is fraction of heat absorbed by the engine which can be converted into work gives the efficiency. Okay, W by Q2. Okay, and this is equal to T2 minus T1 by T T1. Okay, actually this is the heat corresponds to temperature T2. Actually this equation earlier we got this equation, that is W is equal to Q2 into T2 minus T1 by T2. Okay, so that means W by Q2 is equal to T2 minus T1 by T2. Okay, so these two are same. These two are same. Transposition of this Q2 into onto this side, that is denominator, this equation takes that form, right? So W into Q2 into T2 minus T1 by T2. Okay, so this equation can be written, because this equation can be written as Q2 minus Q1 by Q2. How can we write this equation? Okay, so how can we write this Q2 minus Q1 by Q2? Because temperature T2 is corresponds to heat Q2, or Q2 heat is corresponds to temperature T2, and temperature T1 is corresponds to Q1 heat, or Q1 heat is corresponds to temperature T1, right? And then the Q2 is corresponds to temperature T2. Okay, already we know that the cause and effect. Heat is the cause, and which effects can be seen in the temperature. Okay, so Q is heat is cause and its effect is temperature, or vice versa, right? Okay, so this equation can be written T2 minus T1 by T2 is equal to Q2 minus Q1 by Q2. So now in the next step we can write this T2 by T2 minus T1 by T2 is equal to Q2 by Q2 minus Q1 by Q2. Okay, from this we can write 1 minus T1 by T2 is equal to 1 minus Q1 by Q2. Okay, so this is the efficiency of the engine. So efficiency of the engine eta is equal to 1 minus T1 by T2, 1 minus T1 by T2. But no heat engine has not yet been constructed whose efficiency equal to unity. I repeat, no heat engine has yet been constructed. No heat engine has not yet been no heat engine has yet been constructed whose efficiency is equal to unity. That means we cannot construct a heat engine with 100% efficiency. Okay, so eta is equal to 1 minus T1 by T2 or 1 minus Q2 by Q1. Sorry, that is Q1 by Q2. Q1 by Q2. That means from this we can write the Q1 by T1 or Q2 by T2. Q1 by T. From this equation we can write that Q1 by T1 or Q2 by T2 is a constant, value, because this much is decreasing, this much quantity is decreasing from the efficiency, that is this much quantity is subtracting from the unity. That is why we cannot construct a machine with 100% efficiency. Okay, so Q1 by T1 is equal to Q2 by T2, that is a constant. This constant is responsible for not converting whole heat into work. I repeat, this constant is responsible for not 100% conversion of heat into work. That's why this constant is introduced as entropy, okay. So q by t1, or q2 by t2, we can write this q by t, but Carnot's process or Carnot's cycle is what is it called, that is carried out reversibly. So we can write the q reversible by t is a constant, that is entropy, that constant is labeled as entropy. Actually this entropy, already we know that entropy is a measure of disorderness or randomness, and that disorder or that randomness is responsible for not converting 100% heat into work, right? Okay, now actually we already know that entropy is a state function, so we can write that entropy, change in entropy as, okay, so entropy is a state function. So we can define the change in entropy. Delta S is equal to, actually delta S is equal to 1 by T integral Q dq reversible. So let us define this entropy change. Entropy change is integral of all the terms involved heat exchanged divided by temperature during the infinitesimal change, carried out reversibly, right? I repeat, entropy change is defined as integral of all the terms involved involving heat exchanged divided by temperature during the infinitesimal change, carried out reversibly at a constant temperature, right? So this is this gives the change in entropy. Delta S is equal to 1 by T integral dq reversible by T. So after integration we can get q reversible by T. So change in entropy is given by delta S is equal to q reversible by T. So and whose units are what is it called, calorie per degree Kelvin or joule per Kelvin. Usually these are the joule and Kelvin. Temperature units are Kelvin and heat units are joule, and we can write that joule Kelvin inverse. Joule Kelvin inverse is called as entropy unit. This entropy or this randomness is responsible for not converting 100% heat into work. Therefore, we are unable to, or it is impossible to construct a machine with 100% efficiency. It is impossible to construct a machine with 100% efficiency. Okay, 100% efficiency engine is not possible due to the constant that is derived from Carnot cycle, that is q by T or q reversible by T, that is entropy. So this entropy is responsible for not converting 100% heat into work. I hope you learned something, and in the next lecture we will go for the second law of thermodynamics, where we can integrate this concept with the second law of thermodynamics. Thank you. I hope you learned something. If you learned something, please extend your support by like, share, comment and subscribe. Thank you.